If you love translating complex engineering into actual, actionable blueprints, you are in exactly the right place today. We're going to explore 4 distinct utility-scale PV system architectures, pulling the details straight from Eco-Egypt's Chapter 3. We aren't just skimming over high-level theories here, we're going to dig into the real-world hardware, the precise calculations, and the exact structural layouts that make these massive mega-projects actually tick.
Here's our roadmap for today. First up, the isolated BESS plant. Second, solar pumping systems. Third, PV diesel hybrids. And finally, number 4, a massive 4.1 megawatt peak grid connection. Let's get to it.
Section 1. The isolated BESS plant. Let's translate these massive specs into reality. Over on the DC side, we're looking at a formidable 1.1 megawatt peak capacity. Now, to manage storage for complete off-grid, island mode operation, this design relies on 7 distinct BESS units, battery energy storage, of course, with each one rated at 215 kilowatt-hours. To push that energy to AC, we're using 7 Huawei 150 kVA solar inverters. That brings our total AC capacity to a really robust 1.05 megawatts. Operating in 100% island mode is no joke. It means this system has to flawlessly balance the PV generation, the battery cycling, and a backup diesel generator all running strictly in parallel without any safety net whatsoever from a national utility grid.
And looking at the master blueprint, the spatial precision here is just incredible. The layout clearly defines the internal access roads, while your BESS foundation pads and inverter fixations align perfectly alongside the trench routing. The civil engineering is absolutely rigorous too. Your DC and low-voltage trenches must maintain a strict 500mm horizontal separation. Plus, to prevent catastrophic mistakes during future maintenance, they use buried color-coded warning tape, yellow for DC cables and red for LV cables. It's exactly this level of granular detail that prevents absolute disasters on site.
Moving right along to Section 2, solar pumping systems.
So we're shifting our focus now from industrial microgrids to crucial agricultural applications. Instead of relying on one massive pump, which, let's face it, is a huge single point of failure, the engineering choice here is pretty brilliant. We have 125 horsepower total load, but it's divided across 4 independent stations. For just one of these stations, a 35 horsepower pump is fueled by a dedicated 40 kilowatt peak PV array. That's specifically 72 Jinko 535 watt peak modules per station. This setup ensures that every single well operates autonomously, which drastically increases the farm's overall water supply reliability.
Before we even get into sizing these systems, we've got to look at the physical form factors. There's a pretty stark contrast between surface pumps and submersible pumps. Surface pumps are pulling water from shallower sources, and they're super easy to access for routine maintenance. The submersible options, though, are engineered to be dropped deep down into boreholes, pushing water up from some fairly significant depths. And your choice right here entirely dictates your system's dynamic head calculations moving forward.
So, the crucial point is, how do engineers actually size these stations? Well, it all comes down to a really vital formula pulled straight from the source material. Your required flow rate, which is measured in cubic meters per hour, equals the total volume of water demanded by the crops per day, divided by the site's peak sun hours, or PSH. Notice it's not total daylight hours. You size strictly on those specific hours of peak solar irradiance. That guarantees the pump moves enough water while the sun is at its absolute strongest.
Section 3 brings us to PV diesel hybrid systems.
490. That is our anchor number for this specific design. We're looking at a 490 kilowatt peak DC capacity system. But honestly, the real magic isn't just in the massive footprint of the solar array itself, it's actually in the incredibly complex control logic required to seamlessly balance clean solar energy with roaring diesel engines, entirely without causing grid instability.
Let's unpack the hardware stack that makes this hybrid system possible. To handle that 490 kilowatt peak of solar, we're using 4 units of Huawei 115 kVA solar inverters. That gives us 460 kilowatts of AC capacity. Then, for energy smoothing, the design integrates 2 215 kilowatt-hour BESS units, and acting as the ultimate safety net is a massive 500 kVA diesel generator. Getting these 3 totally distinct power sources to play nicely together is an absolute engineering marvel.
And here's exactly how they manage it, through a very strict Energy Management System, or EMS. Step 1 is straightforward. The PV array always feeds the primary load first because it's your cheapest energy. Step 2, Any excess solar energy is immediately routed over to charge up those BSS units. Step 3. The diesel generator is strictly a last resort. It's designed to start automatically only when your solar drops and the batteries are completely depleted. They even use reverse power detection to ensure solar power never accidentally backfeeds into the diesel generator, because that would literally destroy it.
And finally, Section 4, the 4.1 MWP grid-connected giant.
Just think about the sheer scale of these numbers for a second. We are dealing with 4.1 megawatt peak of DC capacity converted by an astounding 30 individual Huawei 115 kVA inverters. But obviously, you can't just plug that much raw power directly into the national grid. It has to be aggregated and stepped up through two massive 2 MVA transformer stations. That pushes the voltage way up to an 11 kilovolt grid connection via dedicated ring main unit skids.
Now, what's really interesting here is the perfect engineering symmetry required at this kind of scale. The plant is perfectly bifurcated. Station 01 and Station 02 are basically identical twins. Each one handles exactly 15 inverters, exactly 3,300 modules, and 2.046 megawatt peak of DC capacity, feeding into matching 2,000 kVA or 2 MVA transformers. This perfectly balanced design drastically simplifies your maintenance and ensures highly predictable thermal dynamics as all that power steps up to 11 kilovolt.
But of course, with that much power comes the need for incredible safety measures. The Detailed Equipment Data List, the EDL, mandates a 4-pole motorized low-voltage air circuit breaker acting as the incomer. Crucially, it has a short circuit rating of 25 kiloamps for 1 second. So what does that actually mean in plain English? It means if a catastrophic fault occurs, this breaker can withstand and interrupt 25,000 amps of fault current. That directly protects those massive 2 MVA transformers and prevents a localized fault from taking down the entire 11 kV national utility grid.